The internet grew and grew and grew some more, and soon they were running out of IP addresses to hand over. CIDR, as we have seen in the earlier video, was one solution to this particular problem. The other solution is network address translation. It stands for NAT. That is the focus of this video. Let's again, like before, start out with an example. Suppose there is an organization with 4,000 hosts. Based on whatever we have seen so far, how many and what type of addresses will you give this particular organization? The answer is you will give 16 Class C addresses totaling about 4,000 IP addresses to the 4,000 hosts. Great, but what if I said I don't have these many IP addresses? Can you manage with a single IP address? Notice the emphasis is on a single IP address. I'm not saying manage with a single Class C address that has roughly around 255 IP addresses. I'm saying manage with a single IP address. Do you think this is feasible? If so, how would you go about it? NAT does exactly this. That is, it manages with just a single IP address. Curious on how it does? Let's see. So it relies on this private IP address space that we covered before. Remember, this address space, you don't have to register with the RIRs. Anyone can use this space. But the problem is these addresses, the private IP addresses, are not routable in the global internet. If a router saw a destination address as a private IP address, it's just going to drop the particular packet. We have quite a few of these private IP addresses. In Class A, they range from 10.0.0 all the way till 10.255.255.255. By the way, these are IP addresses I'm talking about. In Class B, they range from here to here, and in Class C, they range from this to this. In Class C, if the IP addresses are ranging from this to this, how many Class C addresses are there? So this corresponds to 256 Class C addresses, and this corresponds to 16 Class B addresses, and this corresponds to a single Class A address. So plenty of addresses to use. So this organization can use any Class B address in the private IP address space and do subnetting within it in whatever fashion it pleases. It can even use Class A. Since naturally the hosts within this organization would like to access the internet, so what you do is you connect this organization to the internet via what is called a NAT router, and this NAT router has a global routable IP address. It can also have a pool of IP addresses. I was mentioning earlier whether you can manage with a single IP address. Sure, you can. But if you have a few more, by the way, when I say here few, I'm really not talking about thousands of addresses, just a few more, 4 or 5. It can do even better. Now what this NAT router does, it has a global routable IP address and does what is called address translation. This also goes by the name IP masquerading. So what is this address translation? Let's again understand this through an example. So here is the organization that is using a private IP address space that corresponds to 10.***, basically the Class A private IP address space, and it is connected to the internet via this NAT box, which has a public IP address corresponding to this. There are many hosts within this private organization. I've just indicated 3, but there are a lot more. And in the internet, there are many servers. I've just shown one server whose IP address is this. These IP addresses, by the way, match reality. This 103.21.124.55 is actually the address that IITB uses to interact with the external world. And this is the address of a Google server. Address translation is rather simple. So this host, when it wants to talk with the server, it will create an IP datagram with the source set equal to its IP address, which is equal to this, and the destination equal to the Google server, and it is going to send this packet. Now this packet will go, finally it has to exit via the NAT box. So it comes in here, and when the NAT is sending this packet out, all it does is it will replace the source address with this external IP address. This is a routable IP address. So if some other host sends with destination equal to this, it will come all the way till the NAT box. And that's what has happened. Once this packet reaches the server is going to reply with the source as the server's address and the destination corresponds to the NAT box's IP address. So this comes to the NAT box. And now the question is, the NAT box has to send this packet to this particular host. So my question to you is, what state should the NAT box maintain to successfully route this incoming packet to the correct host? Based on whatever I have covered so far, you may be thinking, let me maintain this state. So whenever I receive a packet inward in this direction, I'm going to note down this. I will note down the source as well as the destination of that particular packet. And now when I receive a reply from the outside world, I'm going to match this incoming packet source with this destination. If they match, then I'm going to replace this destination with this. So I'm going to replace this with 10.129.133.10 and send out the packet internally. If this was not what you thought, then you are smarter, because this doesn't work. This is not the only host which has monopoly over the Google server. Other hosts may also want to talk with this, in which case these are the kind of packets that get generated. Now if you are sending these packets out and the server is replying, you're going to get these packets. This was in response to this packet and this was in response to this packet. Now if you see, based on whatever state you have maintained, these both look similar. Who do you send it to? I mean, how do you decide that this actually has to go here and this has to go here? It's not easy to distinguish. So what do you need to do then? You need to rely on some other field to distinguish. Can you think of what this field could be? The port numbers to the rescue. By the way, these ports have got nothing to do with the switching ports. These are the ports at transport layer to distinguish the application processes. So these are transport layer ports. So you can now maintain this state as part of your network address translation table. Notice that I have removed destination here because, as I said, many hosts can contact the same destination and it doesn't give you a distinguishing feature. So here I'm going to maintain port information. So whenever I receive this packet, I'm going to maintain an entry like this. Whenever I see this packet, I'm going to create this entry. Now when the replies come, I will look at the destination port. This matches this. Thereby I'm going to send this packet to this particular host by replacing this with the address corresponding to that particular destination. Similarly, when this packet comes, I replace this with the address corresponding to the particular destination, and this replacement is based on looking at this particular port information and the table. Do you think we are done? I guess from before you know that there is a catch whenever I ask this question. No, we are not done. There is still a problem here. Can you think of what it is? Well, here is the problem. These ports are randomly picked. So there is nothing stopping from two hosts to pick the same source port. And the destination port can also be the same because they are contacting the same server. In this case, whatever replies are coming in this particular fashion, again, they are all identical. The table earlier will not provide you any information on who to send this to and who to send this to. So those table entries, the state entries are wrong. What can you do to solve this problem? So here is the solution. If you are anyway changing the IP address field, let me change the port address field also. So what you do is when this packet comes, you are not only changing the source IP address, you are also changing the source port number. And this ensures that you can maintain uniqueness among all these entries. So you will always ensure that you can distinguish between packets belonging to different flows. So in this particular case, I have mapped this to this and I have mapped this to some other number. Since they are distinct when the server replies, you can quickly map this to the correct entries because these are always maintained to be distinct. In this case, I have also maintained the IP address of the NAT router, the external IP address, because as I said before, if it is operating with a pool of IP addresses, it needs to maintain this information as well. So that's the idea behind network address translation.